What's up, guys? How's it going? This is episode 3 of Large Data Banking edition. We some new stuff going on the stream. I improved my setup a little bit, so now I've got this dual computer setup that hopefully will prevent several of the issues that made it so painful for me last time, and possibly also so painful for you, the viewer, such as laggy computer, laggy stream, unpleasant situation. Yes, holy dark mode, that's a new change as well. This was, I had a request for this. Better contrast maybe, just trying to be a little bit cooler maybe too, because we like being cool when working on databases. So yeah, I think that's kind of those things out of the way. Got to make the whole editor solarized now. I think you're probably right, but you know, maybe you can send me a configuration for that or something like that, because I think this is pretty good. I don't know. One problem is that at this resolution, like the menu bar takes up like half the screen. But you know, that's okay. I don't know if there's too much I can do about that at this exact moment. So yeah, is this music too loud? What do you guys think about the music volume, by the way? Is this like a good balance of voice versus music? I thought that we could move out of the realm of chill, relaxed beats, because honestly, that sort of put me to sleep. So now I've moved on to sort of a driving house soundtrack for the programming this time around, in an attempt to keep both me, the streamer, and you, the viewer, more engaged, more excited. Generally just, you know, a little bit more things. So anyway, I think we'll just keep it like this, volume-wise, and dive into stuff. If the stream is still working, I think it's still working. I think what we were going to do today is continue a little bit of work on partial indexes. Basically, where we left off last time with partial indexes was that we had something that like kind of started to work in like one particular case. I think specifically for the backfill operation, it might have been working, something like that. Yeah, so I'll just do a little bit of a recap of that to start off with, to make sure that we're all on the same page before we keep going. But I think I'm on sort of a random different branch right now. I had some other work in progress that I think I'm just going to pause for the time being, fixing a couple of things with some explain output. I'm actually going to turn this volume down a little bit as well. How about this? Seems like a good mix. Yeah, so I'm just going to sort of stash this stuff out of the way and get back to our last spot. We have a little branch called partial indexing that we're going to check out. Love the beats. Thank you, Dan. So I think what's going on here? I have this work in progress commit, and I think that it does like a whole bunch of stuff. Okay, so how about we start out with a little demo? We're going to compile. I think the whole point of this dual computer thing too is so that this compiling thing will work a little bit faster this time around. So hopefully that's true. And also my computer won't completely explode while doing both video streaming and also compiling stuff at the same time. CockroachDB has joined the chat. Can I increase the font size? I sure could. For you, my friend, really, I will do anything. That's not true, but I'll do some things like increase the font size. Yeah, so hopefully this will finish soon, and then I can kind of show off what happened so far with the partial indexing stuff. And just as a overview again, a partial index, it's an index that has a predicate on it, and it uses the predicate to decide which rows are stored in the index. Normally, indexes store every single row in a table. It doesn't matter whether the row has a null or if it has another value or anything, really. It'll always store every row and let you look up stuff by the column that it's indexing or the columns that it's indexing. With partial indexes, though, we're only going to be indexing certain rows And we figure out which rows to index by running this predicate every time that we insert, update, or make a new index in the first place. So I think what we basically did last time is we added some methods that evaluate this predicate. Maybe I did some of this off stream. I can't exactly remember. I worked a little bit off stream on this project, but not too much. And I think I'll hopefully be able to show off. Oh God. Okay, so there's some debug output that I included here. Let's just forget about that for a second. And I will just make a little table here called A. And I'll give it another column as well. And I'm going to make this index with this predicate like we were showing last time. So create index on A of B where B is greater than, B is less than 10 and B is greater than 3. So if you just ignore this debug output, that's super gross. I think that did something. I forgot to add some rows so we can prove that in fact something did happen. So let's start again. We'll kill this table, make the table again, and then let's insert one row that satisfies the predicate and one row that doesn't satisfy the predicate. So we'll insert a row where B is equal to 0, and we'll insert a row where B is equal to 5. Sorry about all this debug output. Okay, insert into A values 0, 0. So this is going to be the row that doesn't satisfy our index predicate. And then we'll insert one that's 5. So this one will satisfy our index predicate when we make it. Oops. Except of course we have a primary key, so we have to change this. Now when I create the index, hopefully what will happen is that only the 5 row, so this row here, will be inserted into the index, and we can verify that. And so the way that we're going to verify this is by showing that this database is now fully broken, which is always a fun thing to do with a database. So if I go like select star from A where B is equal to 5. First, let's see like how this thing is actually working behind the scenes by looking at explain. And as you can see, it's actually going to use this secondary index because it's emitting these spans, and it's using ABIDX, which is our secondary index. Oops. But I think, yeah, and so since our predicate was satisfied here, I think this should actually work and it should return a row. True. But if we use this other row where the predicate is not satisfied, even though there is in fact a row where B equals 0, I'm pretty sure this should return nothing. So let's hopefully show that this database is fully broken. Yes. Okay. This is a scary state that you would never want to see in real life. Whoops. So again, we're getting nothing back from this query, but if I tell the index or tell the database to run on the primary index, so to use a slower method, it will return one thing. So this is this is indicative of work in progress, right? This would be a catastrophe if you saw it in production. And so what I hopefully was going to do this stream, well, there's two sort of big work items left to do for partial indexes, I think. I think one of them is making sure that this same thing works for inserts and updates. So if I were to insert a new row, I think that I didn't get to evaluating the predicate on the insert side of things. And same with update. If we're changing a row, and we have to check that the new version of the row is going to be inserted into the index or not. And similarly, yeah, so for insert and update, we've got to check these things. And the last kind of step that is going to be hard is teaching the database not to use this partial index in the case where our predicate cannot be satisfied. So in this particular case, we know, since we've pinned B to be 0 here in our filter, we know, well, we should be able to know that since our index is sort of like predicated to never contain that thing, so 0 is not contained in the relation here, like the database should never use that thing. And I'm not exactly sure, yeah, that's sort of optimizer work that, again, I'm not as familiar with doing, but we'll see. So those are kind of the two big work items. One big piece left to do in the execution engine, and then one big piece left to do in the optimizer. So that's kind of that. JMCE, welcome to the data bank. Oh, did I miss an alert? Oh God, that's not acceptable. I need to figure out how to get the alert sound to ping in my headphones or something so I can say thank you when that happens again. But until that happens, thank you, Jay. I know who you are, but thanks anyway. Cool. So I think why don't we go ahead and figure out now what we've done so far, maybe a little bit more, just to help me remember what the heck is going on here. So I'm just looking through this sort of work in progress diff thing, trying to remember what the deal is. Okay, so I think what I did, let's see. I think I like basically added some predicates threaded through in various spots. So I gave the index a new partial index filter member field thing. That is where we store that predicate. And might have done some other stuff. Here is the index backfiller. Index backfiller now has a list of partial index filter expressions, which I guess is our list of predicates. One per added index that determines for a given row whether that, right? Okay. That I kind of remember. And then over here, we've got some more index backfiller stuff. I think this is where we link up the row to the predicate. Here we have a little bit of fun debug output. Question is, what did I end up doing for the actual inserter? This text is like too big. I like can't really even, it's like just really big. So I'm making it smaller. Sorry, everybody. Let me know if it's the wrong size though. Yeah, I think basically I just didn't thread the right stuff through the inserter part. So let's see if I can. I think the entry point that we want to look for is this like encode secondary index entries thing, right? My neon cat needs to index a little bit more. Okay, there we go. So I think this thing probably comes with something. No, this one comes with something. Encode secondary indexes. It now comes with something called partial index predicates, right? Yes. And the question is, who calls this thing? And can we edit all of them? I think this is the one that we probably already did edit, right? It comes with partial index filter expressions. This will have been populated during backfill, so that's during index creations. But then I think the other use case, which is this helper guy, we're probably passing nil to it or something. Yeah. So this is kind of what we're going to start editing this time. We need to, instead of passing nil for this partial index predicates thing, we actually have to pass something a little bit more intelligent, like the actual partial index predicates. So the question is like, how are we going to end up doing that? And I think to figure that out, we need to remember who calls this thing and when, and what do we have when these things are called. Sort of a fun threading problem, at the very least. Row helper. Oh yeah, so I sort of actually did start messing around with this. So the row helper is this thing that we use all over the place. I think it's used for all inserts, updates, and deletes maybe too. So it's sort of a common piece of code that we use for everything. Hey, Jeffrey. Jeffrey, nice to hear from you, my friend. John Wiltshire Gordon, welcome to Large Data Bank. I don't know what please means, but I love to hear it. What's the bailout? That's another question that I have before I continue into partial index filter expression messing. I think what's happening here is that actually we do compute these already when we make one of these, but maybe we just don't thread it in the right spot, maybe. It's a suggestion. What? The data bank bailout. I see. I like that. I like that. That's a pretty funny joke, I think. Is this data bank too big to fail? I'm guessing probably not. I think this is a really small data bank. Yeah. So what do we have here though? When we make these things, we make our new row helper. Do we yet have the things that we need? This is where I came with this debug information stuff. That's right. So let's see, what does it do? It returns a slice of evaluable expressions, one per index in the input, that represent the partial index filter for that particular index. That seems right. I think I wrote this last time. Maybe it was wishful thinking. If a particular index does not have a partial index definition, there will be a nil in that position in the return slice. So I guess this is why I'm logging all this stuff, because I was just trying to remember whether things were actually getting inserted in the right spot. And out of curiosity, what is happening with that? Why don't we do a little bit of a test and see if things are getting logged where we expect to. Workshopping catchphrases. That's cool. All right. So let's go ahead and recreate our little sample scenario again. Create our table, create our index. Now what happens, what does this crappy debug thing print out when we insert something? Insert into a values 0, and let's put something that does satisfy the predicate. What happens is that we do get some things getting printed out, which seems promising. This sort of seems like this method did in fact receive the right partial index predicate, which means that things are kind of hopefully getting set up right. And what about if we did an update? Update A, set B equals 7, whoops, where A equals 0. We also get something. That's fantastic. So something's good. Something's good. And I think maybe the missing thing is that we just didn't keep passing it further down into the belly of the beast. So let's see if we can do that now. We set our row helper. We have our row helper later. And then I think we just never use it. So let's see. Where do we actually have to use this thing? It's down here. Encode secondary indexes. I think, can we literally just... How come I didn't do this last time though? I'm very suspicious of this. Very suspicious of this. But let's try that out. Programming. It's just a matter of replacing nil with variables that already exist. That's truly fantastic. So what's up with everybody? Give me something. Say some funny, give me some other catchphrases. How about? You know, I think improv comedians have it hard. They have to wait for somebody to say something. Maybe the compilation will take a little bit less time this time, since I'm only changing one thing at a time. My cat is stuck behind the stove. I'm sorry to hear that. I don't exactly, stuck cat syndrome. Yeah, I don't have a cat. I think that would be a hard thing for me. Create our index, we're gonna insert, and hopefully we'll, okay, this is great. Back to, back to something that we know and love, which is broken stuff. How about that? So what happened here, what did happen here? What happened is that we tried to evaluate an indexed bar and it crashed because something. So I think probably what happened is that we forgot to like hook up the row values with the evaluator machine thing. So we're trying to maybe evaluate this predicate, but we didn't like set the values for each of these variables here. As long as you don't have to rebuild the admin UI, it's Gucci. Yeah. So, oh, I see. Well, I think we just never really set up a, we never set up our index bars because we're passing a nil eval context here, I think. So the eval context is this thing that's supposed to help with a lot of things, but one of the things that it does is that it contains the mapping of row values to column names, basically. So if you're evaluating a predicate, it helps that predicate fill in the blanks for the column values that it needs. Yeah, so I think we've just got to pass something in here. That should be fine. I think we might need to maybe like create one from scratch or pull one from thin air since we don't really have one available. Where was the last place that we had an eval context? Presumably like there's plenty of these things floating around because people need them all the time. Anytime that you evaluate any kind of expression, you need to know about eval context. Maybe I just have to really get it from far, far above, though. C has one. What's C in this case? Oh, it's just some random. Maybe when we make a row helper, we should really pass in a eval context. Maybe that's a way to do it. That seems a little bit principled. Otherwise, we would have to give every little struct its own eval context. Null bitmap says, I think you should add the expression in the optimizer. Add the expression in the optimizer. So you're saying that we could like make a little special projection slot and have the row inserter just receive a Boolean, like how check expressions work. Right. That could be a way to do it. I do think that that would require effort, but maybe it's sort of principled effort. Yes, I think maybe what happened last time is that I decided to do it this way because I knew how to do it this way. But I think that you're probably right. So I think last time we were talking about this mutation builder business, I sort of quit this because I was overwhelmed with its complexity. But maybe we can sort of figure out how it works again. Check ords. Synthesizes a Boolean output column for each check constraint defined on the target table. That sounds legit. Oh yeah. So I see. I never even put our little guys into our index predicates into the optimizer's representation of the table. I think what null bitmap's saying though is that the optimizer doesn't actually have to figure out the Boolean result, because that would definitely be impossible, but it can make a projection that figures out the result. So in other words, like it'll insert this little fake projection that the user never sees. And then you can look at that thing inside of the insertion code and then project it out later. Which I think is cool. I think it is, I mean, it's a little bit weird. Like what happens when you have a check expression? Do you actually see that in the explain output? That would be sort of fun. Like, does the optimizer tell you about it? A int check. How does it a greater than 3? Do I have to put parentheses? Explain insert into a values 5. So the I guess this thing doesn't do it, but maybe the optimizer explain version does it. But in the case where you do have the row statically, you get plan time evaluation of the predicate for free, which is cool. Yeah, that is cool. So this also doesn't have it. Maybe the verbose version has it. This check columns. That is something kind of interesting. All right, well, yeah, let's forge ahead. Forge ahead. I think maybe the first thing we can do is add the check constraints to the optimizer's understanding of our schema. That seems like something that I can easily do. Where is this implemented? Op table. Active checks. So I guess I could sort of make a new thing like this. Yeah, this is another thing that I didn't really mess with, was this nice immutable table descriptor interface guy. I think I just sort of slapped something onto the main table descriptor without making any sort of pleasant getter And I don't think that that's a nice thing for anybody. So I should probably improve that as well. So I think I'll do it maybe. Oh, it's also inside of index descriptor though. Do we have an immutable index descriptor thing? I feel like no. Yeah, so it's a sort of a question of what to do with that. Another question is, does the optimizer have its own conception of index descriptors? I feel like it does, probably. Table cat, what is it? Cat something? Cat.go, catalog.go, index, catalog, resolve schema. What is all this stuff? Index, here we go. Okay, so I think what we'll want to do here is add some representation of these things. And the question is, what form does the other one get returned in? Maybe an opt dot something. Expr? It returns a check constraint, which is a little struct. It's a string. Okay, let's make a new thing for this then. So we'll call it a partial index predicate. No, but we really need one. You should add it. You're probably talking about the immutable index descriptor thing. Yeah, I should add that. That's like a huge thing though. Boy, that's like so much work. I'm very scared of that. I think we definitely need to desperately come up with some better interface for tables and indexes in the database, because it's right now like a half completed project, I feel like. So partial index predicate contains the SQL text for a predicate, for the predicate on a partial index. The predicate determines whether any given row, I see, well, I guess we sort of, the predicate determines whether any given row belongs in the index or not. Great. And then I guess we can sort of do this little pattern here, because that's how things are done in this world, where we'll have a, oh wait, no, we don't need a count. We only have a, it's like a yes or no sort of thing. I wonder, do we just return like empty? I'll just do that for now. Partial index predicate. Partial index predicate returns the predicate for this index if it's a partial index for the empty struct. What have we, default? What's the word for this in Go again? The uninitialized struct if it's an ordinary index. Maybe we could put a sort of Boolean for this as well, but I don't know if that's really how we do things in this place. Is inverted. Yeah, it is sort of maybe kind of how we do things. I don't know. I'll do it that way. Whatever. Is partial index bool. Is partial index returns true if this index is a partial index. In other words, no, whatever. We'll just do this for now. But look at how nice all these documentations are. I'm skipping this song. All right. So I guess now we just go implement these things. And of course, now my editor forgets where these things are implemented because that's how it works. I always forget how to deal with this. So usually what I do is I just comment these out and then I navigate and then I can come back later. It's in optcatalog.go. Maybe we can use this little fancy, no. So in opt index, we're going to want to implement these new methods. And I think we can do it just by saying implement index. Look at that. Love that. Index. Okay. So we've got these little stub methods. And I think, does this thing, let's see, does it cache everything or does it sort of reach inside a table descriptor? It looks like it caches it. So I guess what we'll want to do is include the information in this thing. I guess we'll just include our new struct for this thing, which was called partial index predicate. This guy. Where is this check constraint one used? This one probably, it's stored in tab, which is opt table, I think. No, it's in, this is a test one? So maybe we just synthesize these when we return them. So in this case, this is also test catalog. In this one, yeah, we just synthesize it. That's fine. Okay, so we'll just synthesize these ones as well. And they're synthesized from, oh, okay, yeah, so we literally just reach into the descriptor, which means I don't have to do anything. I can just do it on the fly. So this is gonna return true if oi.desc.partial index. Ooh, this one's called filter, that one's called predicate. I don't like that, I'm gonna fix that. Predicate is a cooler word, so let's go with it. Predicate. It's more accurate too, I think. Okay. So that'll get fixed later, but in the meantime, actually, let's just quickly recompile the protobus right now. So the idea with this is that, yeah, protobuf, you sort of write these things in a definition if you're not familiar, and in Go anyway, it generates code that gives you sort of a memory representation of these messages, and these messages also can be encoded to bytes for saving on disk or sending over the network, which is pretty important in a distributed database and also in many other applications. Protobufs are, they're like pretty good, I think. They're pretty good. So back to our opt table. No, man, I'm so bad at remembering the name of this file. Opt catalog. So we're gonna return true if we have oi.desc.partial index predicate is not equal to the empty string. And then here we'll just return a cat.partial index predicate. This cat, this cat is not stuck behind any stoves. So there you go for a callback. And this we'll just kind of take this and hide this little guy. Very simple, very boring, honestly, very boring. But important, plumbing is important. Do we comment these things? Yeah, we say, that things are part of interfaces. To make it obvious where to go for documentation, so you don't have to repeat yourself. That's great. Is partial index is part of the cat index interface. And same goes for partial index predicate. Love the reincorporation, my man. Thanks. Okay, so I guess the next step now we've enhanced our catalog. We probably, yeah, that's all we have to do, I think. The next thing I think is that we actually have to use it. And I think that these will get, I mean, yeah, we didn't add anything to any struct, so this is just always gonna be usable now from any opt index. So the question is, let's go back to this mutation builder thing and see where this comes from. let's take it as the example, this build insert. We make an insert, we do a bunch of stuff, and we just add columns to the input. That's so simple, so elegant. Much more elegant than what I was doing earlier. Hello, A Woods 187. You missed, you know, programming. Little intro, little chatting. I'm glad the video quality is better. It's all because I have 2 computers in the mix now. Super advanced. Okay, so I think what we'll do is we'll just sort of make another copy of this for our index predicates. And it really should be basically the same thing. So we'll just copy it and edit it. So we'll call it add partial index predicate calls, and we'll make up some stuff for this. Add partial index predicate calls synthesizes 1 Boolean column per index on the table we're inserting in to that has a partial index predicate. The purpose, or later, the insert execution code will pay attention to the results to the value of these Booleans. Let's just use the word use. How about instead of pay attention to? Use the value of these Booleans to determine whether or not to actually insert a value for that partial index. No, insert any given row into the partial index. So basically, we only want to do anything if our tables, oh, I guess we actually sort of need a loop here. We need, for every index in the table, let's see, index count. Yeah. For every table in the, excuse me, for every index in the table, we're going to check something. So the index is going to be mb.tab.index of I, or is it weirdly like I plus 1? No. Yeah, still working on partial indexes. I think last time I was intimidated by their difficulty, but truthfully, I think a lot of that pain just came from my computer being really slow due to streaming and editing at the same time. This is much better today. I'm feeling great. Hope you guys are feeling great too. So we're going to say if index dot is partial index. If it's not a partial index, we're just going to continue along in our loop. And if it is a partial index, then we have to figure out how to deal with this thing. We have to sort of inflate the expression and then run it. Hopefully the optimizer will figure out the hard parts of that for me. Looks like it's gonna. So first we will, I mean, yeah, it's just definitely weird that we literally reparse this thing from the index descriptor each time, but you know, that's life. MB, let's see, no, come back. Index dot, let's capture this thing. Predicate. Predicate dot predicate. We're gonna return, guess we need to have, do we panic? Yeah. Isn't that so fun? The optimizer will catch our panics. Exception programming. So much better sometimes. All right, anyway, so we panic if there's an error. If there's not, we have an expression that is chilling. And we guess we will try to type it. Then we'll add a little column and move on with our lives. Okay, I don't know what this alias is for, but let's make one. So we'll call this partial index predicate n. I guess we sort of want to count up our partial index predicates, or we can just link it to the index ID, but I feel like it's cleaner to not do that, and we'll just have another n partial index is equal to 0. Audio got funky? Still funky? Is it okay? Are we dead? I don't know. Maybe refresh? Yeah. Let me know if it fixes when you refresh. Otherwise, I'll do something drastic. So we've got our alias set up. We're going to put it to the nth partial index thing. And then we'll type our expression. So this is making sure that it's actually going to be a Boolean. This, of course, is going to be checked earlier, but we have to check it again because that's just sort of how things work. We have to give the expression a type. I don't have Corona yet. Me neither. This is, I don't know, this is not a, this isn't like a stock trading stream, A Woods 187. So no comment. This ain't our Wall Street bets. So we're checking that our stuff is a Boolean, and then I guess this thing is going to be, gives us a typed expression. We had an untyped expression, and now we had a typed expression. And then I guess this is sort of probably the magic that's going to be adding a new projection. So how does that work? Add column adds a column to scope with a given alias, type, and expression. It returns a pointer to the new column. The column ID and group are left empty so that they can be filled in later. Okay. Okay. Well, this seems like it's going to be completely the same. So, and our scope, what is a scope? Disambiguate names so that the references in the constraint expression refer to the correct columns. Is each table column name? I don't know why we would need to do that. I guess in case. So that references in the constraint expression refer to the correct columns. But this is all happening before we do anything. So I don't really understand. I sort of thought it would be like if you had anything that was called check I, then it would make sure that there wasn't something called check I. But I guess it has something to do with something else. Damn coronavirus, eventually consistency is too long. Just get out of here. With that, I don't even know what that means. So I think I'll just, well, ranges over the scope. Okay, let's just read what it does. Determine the set of scope columns that will have their names preserved. So for each of the columns in our table, we check to see if it's in our scope. And if it is, So we're setting columns to be anonymous so that they cannot be referenced. Oh, maybe it's so that, maybe it's, is it that like somewhere else, if you had a column that you needed for a check expression that wasn't needed by anybody downstream, we have to ask for it, but then we have to let nobody else reference it but the check expression, maybe? Maybe it's something like that. I'm gonna try it out again to see if that makes any sense. But this probably just doesn't give us enough information to tell us whether that's true or not, honestly. Wait. This doesn't make any, it would have to be like an update, I think, right? So let's drop this table. Let's make a new table that's like a int, b int, c int, and then we have a check expression on C that references something in A. So then if we explain update A set C equals 3 where B equals 2, notice how nobody needs to see A except for this special check expression. So maybe like, oops, go away debug information. No. We just have to write it again. Update A set C equals 3 where B equals 2. Explain opt verbose. All right, so in this case, something a little bit more complicated is happening where we're searching A, we have a filter on it, and what we need, oh, maybe we want a returning clause too to make it a little bit cooler. Returning C, I guess. So we need to fetch A because there's a check constraint on C that references A here. The select has these columns. The projection, here's our special guy that we were searching for. It's got this check one thing that we synthesized out of nowhere. And we made a column 9, which is, what the heck is that? Well, I don't know what that's about. Column 9. I think it has something to do with what we were just talking about, but I don't exactly know how to connect the dots yet. Because I think this check one guy is our Boolean. Maybe, can I get like the types of these things? Is it the const 3? Maybe it's the const 3. Const 3, projections. I didn't see this. Yeah, okay. Well, I guess that's fine. I guess I still don't exactly, the update mapping tells you that column 9 is the value being assigned to C. Update mapping. Look at that. You just have to know where to look. That's cool. Okay, so then I still don't exactly understand what the deal is with this this other thing. The disambiguate columns. But maybe it just doesn't like kick in unless it's in a sort of a weird case. Whatever, let's just do it. I hate doing stuff like this, but you know, it's okay. Disambiguate names. I think this is called cargo cult programming. Scoping nonsense when you parse expressions late in the lifecycle of the query freaks me out and I don't understand it. You and me both, buddy. Didn't you write this code? No. Wasn't you. Okay, so let's figure out how to make this scope then. Outscope is the thing that comes before us. Outscope contains the current set of columns that are in scope as well as the output expression as it is incrementally built. Once the final mutation expression... Oh, I see. This is just in mutation land. Once the final mutation expression is completed, it will be contained in outscope.expr. Columns, when present, are arranged in this order. Oh my god. There's a little thing. I have to deal with this. Oh. That is truly... I think this is upsetting, unfortunately. This is one of those things that definitely displeases me. Like, whoops. Come back. Like, do you just have to keep making stuff like this forever? The more complicated your optimizer gets, the more like weird ASCII art diagrams come into it. Okay, insert, fetch, update, upsert, check, and partial index. Predicates. There's got to be a better word for this. A little concise way. Index preds. How about? That's more concise. Because if there's a predicate on the index, you know, it's gonna be partial. That is for sure. Maybe I can group it with the check one somehow. Well, look, now they're grouped. So you're saying we could come up with some sort of thing that's like just like a predicates group that has various predicates. You know, and there's going to be something similar too that comes up eventually, I think, which is the... Well, actually, wait a minute. Where does the computed columns go? Where do the computed columns go? I would assume that naively computed columns would go into the exact same spot as this. But add synthesized calls. Like this has to... What is this? How come there's no little... Oh my goodness. They're in the insert... that makes sense. Yeah, that makes sense. So the idea with that, I guess, is that since... So, yeah. Computed columns, you just don't have to specify them, but like from the database's perspective, it's really just the same as a regular value, regular column value that somebody put a value for. It's just, there's a little higher level machine that does it. Okay, that's not that bad, I guess. But I think that when you get to computed indexes, you will have to have another thing that's similar to this. So maybe. Where was I? What was I doing? I was editing that little diagram. Outscope. Okay. So columns when present are arranged in this order. We're adding a new thing. Maybe we can collapse these things later, but I don't know. Each column is identified by its ordinal position in outscope, and those ordinals are stored in the corresponding scope ords fields. See below. Delicious ordinals. So we got something called like partial, or let's just, partial index predicate ords lists the outscope columns storing the Boolean results of evaluating partial index predicate expressions defined on the indexes of the target table. Its length, oops, oh my God. Did I just make an its typo on screen? That's embarrassing. its length is always equal to the number of indexes that contain, no, the number of partial indexes on the table. This is among the more gnarly parts of the optimizer. Partial index predicate ords. Cool. Oh no. Oh Lord. What? What? All right, so there's some kind of crazy magic going on over here. We're making a slice that is the length of n times 4 plus the number of checks. Okay, fine. I guess that's not that crazy. It's pretty weird though. It's pretty weird. It's pretty cool, I guess, but it's a little weird. Okay, so maybe what we really ought to do is come up with like a little bit of a helper here, that since we're going to be referencing the number of partial indexes frequently, perhaps we ought to make a helper for it. Maybe we could cache it on the immutable table descriptor. Do we ever do that sort of thing? I feel like we probably do. We should be doing more of it. Where do these things get made? New immutable table descriptor. Write only call count. Yeah, this is the sort of thing. Okay, so like partial index count. Is the number of indexes on the table that have a partial index predicate not, yeah, whatever. Let's just keep it like that. So now we have to remember how this stuff works. Basically, we're gonna want to figure out, we're just gonna want to count stuff, but we also have to add up the relevant mutations in which so sometimes tables are in a write-only state, and sometimes they're in a delete and no. Sometimes they're in a delete-only state, in which case you're only allowed to delete stuff from it. Sometimes they're in a delete and write-only state, which means that you can both delete and write, but you can't read. So the question is, for our purposes, when do we want to consider these partial indexes? Do we need to consider them when we're in a delete-only state? Yes or no? I kind of think we always need to consider them, maybe. Yeah, I think we always need to consider them. Thanks, chat. So we're going to say that first we're going to iterate through the indexes for I in range table dot indexes. If I dot, if index is equal to table dot indexes of I. Don't need those allocations. Index dot partial index predicate is not equal to empty. Then we say desk dot num, desk dot partial index count plus plus. Count up the number of partial indexes. Now in our mutations, we scroll through each of the mutations. If it's an index, I mean, this is weird that we have to like insert the same code in all of these things. I guess we could conceivably just have another loop, or we could invert the direction of these things. So like we're going to be switching on the index versus column part first, and then the delete and write only part second. Do we need to generate scans for partial indexes ever? I mean, I think ideally, yeah, you would be able to generate a scan for partial indexes, right? Because, like, for example, if you only wanted to index the positive integers on your table, and then somebody did a range query and it was part of the positive half of the integers, then you would definitely want to use the partial index. Mystery meat seems gross. Seems tricky to ensure that your predicate is true on all elements in the scan. Yeah, I mean, I think essentially the way that this is going to work, if I had to guess, not that I know exactly how to do this, is that like you compare these constraint span things. The optimizer has these, it's kind of like, you know how in explain, you have this like actual concrete span thing that has numbers in it. In the optimizer, there's sort of a logical span equivalent, and I think you can like just check to see if their intersection is like, what would it be? I guess if you'd be checking that the partial index completely contains the like scan predicate. I think it's just sort of like some set intersection stuff. Yeah. Okay, so for this thing though, basically, all right. I'll just do another loop over it because loops are cheap. I mean, but I think while I'm here, I'll just fix this because this is causing sort of some extra pointless copies and stuff like that. If there's a hole in the middle of the space to the expression, then like you would still notice, because this containment set relationship thing will definitely notice the hole. You know, we just have to sort of rely on this set containment operation thing that I'm pretty sure has already been defined on constraints. All right, so we'll loop over our mutations again. And we'll say, we'll basically just be switching on this column state. If m.getColumn, no wait, index, not column. Index is equal to m.getIndex. Index is not equal to nil. Then, wait, yeah. If index.partial index predicate is not equal to empty, then we're gonna do our plus plusy guy over here. Desk.partial index count plus plus. All right. So now back over here in our mutation builder. Oh, I guess we want to make one other method here, which is our, I guess it's sort of going to be like, yeah, here. Partial index count int. Partial index count returns the number of partial indexes on this table. The number of partial indexes always includes the right and returned. Yeah, I mean, I don't know. Let's just assume that we want to return all of them for now. So the number of partial indexes returned always includes the public write only and delete only indexes defined on this table. Let's fix this typo while we're here. Okay. And then we'll go back to our opt catalog and we'll implement that guy. Partial index count. Whoops, we want to put this next to the index ones, not the column ones. Partial index count. So then we just return ot.desk.num. Wait, partial. What? It has to be exported. Or maybe I'll make a method for it. That'd be a cooler and better thing for me to do, perhaps. This is just, I don't even know. I think that there's definitely something weird with this because I think that it's going to get confusing with the delete and write only ones, but I guess we'll just forge ahead for the time being. Okay. Actually, let's just, yeah, partial index count. Okay, so let's go back over here and we're gonna go into our opt catalog and use that guy. So down here, we can just return our partial index count. Great, simple. Oh, I think we also should go to our test catalog guy and just fill those out while we're doing this, because otherwise I think things won't compile later. Yeah. Okay, implement the opt catalog. No. Table? Yes. Partial index count was missing. And then we'll have to do the same thing for index. I'm not sure if we're actually going to need to like implement. We probably will. We probably will. Where is our... Here it is. So give this guy the new interface methods that we defined on cat index as well. And these will panic when we go to test, which is fine. We can just fix it at that point. All right, so now what we're going to want to do is go back to this crazy zero allocation machine and start, you know, incorporating things. So I guess we want to, okay, what is going on? We're making n times 4 plus tab.check count. So we guess we just want to add in our partial index count. This is honestly super sketchy, but, and then like this number here is like n times 4 plus tab.partial index count. I don't, no, tab.check count. This is gnarly. This is so gnarly. And then here we're gonna set our partial index predicate ords. Yeah, okay. So then I think we can go back to our method that we were implementing that actually inserts the special column. And we can make our scope, our projection scope, which adds, I see. So we're making a new scope and we're gonna, what is dot replace? Replace creates a new scope with the parent of this scope as its parent. Oh, okay. The parent of this scope is its parent. Okay, so I see, replace, that sort of makes sense. But I guess it just gives a fresh empty scope. So that's why we have to reappend the columns from the scope. Scope. And then the point is that we're adding these new columns to it. So scope call. Yeah. It makes a sibling scope if that's helpful. Yeah, it's sibling, but it's empty. It's an empty sibling scope, which is a little confusing because replace like sort of implies that it would, well, I don't know what it implies, but it's all good. So next up, we're going to build scalar. We add a column, and then we build a scalar. Okay, build scalar builds a set of memo groups that represent the given scalar expression. If outscope is not null, blah, blah, blah. Okay, wait, let's go back. This is where we, see, this is the weird thing, is that like, why do we pass this both into build scalar and add column? Add column adds a column to the scope with a given alias type and expression. Oh, okay, it's just sort of, this scope column expression is really just for like, I think it's just like for looks essentially. I don't think it actually gets used, probably. So this build scalar thing is the actual guy that's adding it to the memo data structure. Yes. All right. So we'll grab these guys now that we understand them. So I think essentially we've maybe built the Booleans into the spot now, and maybe we have to sort of finalize it somehow, and then later we can just use them, hopefully. Construct project for scope. Construct project for scope constructs a projection if it will result in a different set of columns than its input. Oh, that's nice. So it sort of prevents the pointless projection problem right when you're making it. Either way, it updates projection scope.group with the output memo group ID. And then we replace it. The outscope goes away. Pleasant. Pleasant. Okay. So maybe we can just call this guy now in insert and we'll see what happens. I think we'll probably also want to, you know, we should probably like put this into the same method, right? It's sort of like add check constraint calls and other things. Well, whatever. Well, maybe we'll do that later. Add partial index predicate calls. Add any partial index predicate. Boolean columns. Predicate Boolean. I think what we'll also want to do is like add something to the explain output to make sure that we actually can debug what we've added. So let's actually go ahead and check out who else. Well, how? No, maybe it's already done because I think like this alias thing is the thing that gets included in the output. Let's see what, let's get rid of this annoying debug crap. I don't like it. Hi from, this is like debug information when you're trying desperately to get something work. You put a stupid name. That makes no sense. Very spammy. Okay, what happened here? Computed expers.go. Oh, I think I renamed this and didn't rename it everywhere. Let's fix that. Partial index predicate. Probably again, partial index predicate. Look at that, 5.4 second build of something to do with web things. That's not that bad, but maybe it's still going. Edit those proto buffs. Get a big recompile. Build short. I just like the web UI to be in my binary, you know? It just makes me feel a little bit warm and fuzzy. Even if I don't use it. What do you think would be faster, waiting for this to finish or killing the whole thing and then running build short from scratch? Probably running build short from scratch, honestly. I don't know. Let's while this is going, why don't we figure out what's next? I think that the insert code has to know about this, so let's go check it out. check. Oh God, why is this like weirdly highlighted? This is not right. Okay, wait. Insert.go in SQL. This is what I want. Check, 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 check. What? Who knows about this checking business? Maybe it's the row check constraint. Okay, something's not finished anyway. I need to keep fixing some references that I forgot to do. I could have done this in a smarter way. I feel silly. Now I have to go fix a bunch of broken references. Uh-oh. I don't want that sound to be being made. Let us quit that thing. Partial index predicate. And opt catalog needs to be, something's wrong. Opt catalog cannot use opt virtual table literal as, okay, all right. I forgot to implement the thing on opt virtual table. Let's go fix that. Opt virtual table gets new things now. We'll leave them panicking for now because I don't think you really need to mess with that too much. Opt virtual table, opt virtual table, opt virtual table. And then one last thing in create index, create index. Fix this. Okay. Okay. Sunk cost fallacy. Okay. The cost was sunk, but now it's not sunk. It's unsunk because I'm starting from scratch. I'll do the fast thing. Oh man, it really is a lot faster, isn't it? But I think we already finished building the web UI, so like, don't you want that web UI? That beautiful web UI. So fresh. It really looks fresh, by the way. Have you guys seen this? Like, it's different. I woke up one day and then it was different. Oh, but now I've got the, I can't even show it off because look what you guys made me do. Look what you guys made me do. Anyway, so what happens when I mess around now? So we're gonna make a int. We're gonna make create index on a of a where a is greater than 5 and a is less than 10. We still have some debug information, that's fine. And then we're gonna do an explain insert into a values 3. Okay, it's broken. That's cool. I expected that. What about an explain opt though? Maybe that, no, still broken. Add partial index predicate calls. Let's go figure out what's broken about it. Doing some panic-driven development. I love that so much. Oh, I'm doing some, I just was referencing the wrong, this is what happens when you don't type out the programmings from scratch. You just edit the wrong slices. Okay. I'm doing normal make build because I want to show off the new web UI, which is very beautiful. It's very beautiful. I don't know when it happened, but it was maybe during January when I was gone. But it's like, it's all flat. It's like designy. It's pretty cool, honestly. I'm into it. All right, we'll spin up our demo. And I think we've got a link to click. I think that my screen resolution is very large, but look at this. I mean, it's fresh. It's fresh. Check out this amazing title. It's the v20.1.0 beta.1.128G64 dirty. I think that's a great name for a binary, frankly. Look at this. It looks really nice. It looks really nice. I'm into it. I'm really into it. Anyway, okay, goodbye. Let's do our test again. Create index, and then we're gonna do our insert. Still broken. That's fine. We probably didn't like allocate. I thought we did allocate this. Hold on. Index out of range 1 with length 1. It's the same line. I thought that we did this right though. We initted it. And we added, did we not What? Maybe this thing's returning the wrong number. This is probably the problem, right? This is a test catalog. Partial index count. Partial index count. I mean, I don't know, dude. I don't know, dude. Are there more than one way to make an immutable table descriptor or something? Well, let's log a couple of things then, I guess. If you make an opt test for this, you won't have to compile all of CRDB. What? Are you saying to me that you want me to make an opt test? That's crazy. I do want to figure this out, but yeah. I mean, you know, this is a compelling thought. Let's see if we can find out where that might live using only the powers of our mind. We can make a, we don't want to mess with that. We want to mess with like this maybe. Checks. How about insert? Insert. Do we have a check constraint up in this? Oh, heck yeah. Okay, let's make a new table. We'll call it partial dashes allowed? I don't know. I forget. Partial indexes. A int primary key. Let's just make a single. Let's make a couple. A int, B int, index on A where A is greater than 0. Index on B where A is greater than 0. Got a little crazy. And then we'll go way to the bottom and we'll make a thing build. Is that what we want? Build, maybe. Insert into, what did I call it? Partial indexes. Values 0, 0. Okay, let's see what happens. Make test. SQL opt builder. I don't know. I never do this. You'll have to add support for this to the, oh, this is probably, yeah, implement me. Okay, that's easy though. No probs. What is the use of an index where the constraint is on a non-indexed or stored column? I think it's this, the example from last time was kind of about users that are active or inactive. You could imagine wanting to index users on their ID, but you don't actually care about indexing them at all if they're inactive. So, yeah. Does that make sense? Test table? No. Opt. Test catalog. Right. All right, so what's the deal with the test table? Does it have indexes? Yes. Okay, so we have to make a little partial index predicate guy in here too, I think. And in the test catalog table, are there check constraints sitting around? Yes, there are. So we just want to clone this approach. Index, where are you at? Index. Oops, not like these. Cat dot partial index predicate. Partial index predicate. Index predicate is non-default. Default? Is that really what? Is the partial index predicate is set if this index is partial. All right, how about that? return ti dot partial index predicate dot predicate not equal to this. And then this is return ti dot partial index predicate. Ti dot partial index predicate. Well, I think this should still probably fail because, like, doesn't there need to be something that sets this? Definitely. Who is the one that does that, though? Add index. Partial index count comes first, though. Well, yeah, that's fine. Partial index count. In our test catalog. We'll just iterate, I think, because this doesn't have to be fast. tt dot partial. Oh no, look, everybody does this cooler thing, so we'll do it too. Partial index count int. Oh, okay. If def dot, what? No, don't, oh God. If def dot, what is def? And why doesn't it have a partial index predicate area? What? Oh no, I haven't done something. Okay, I have to improve everything now. This has to have, where did my partial index predicate go if not on this thing? I don't understand. SQL.y. I only, filter! I keep calling it filter and, okay, my predicate is way cooler. Partial index predicate. Let's switch all of the versions of filter to use predicate, first of all, just because we feel like it. Okay, and we'll have to go, oh, it's in create index? I see, it actually has to be in both spots, annoyingly enough. Partial index predicate. Yeah, refactor it all. So where is this thing? Create index def. No, create index table def? Index table def? All right, so basically, yeah, the idea here is that we can make an index in one of two ways. We can either create an index with the word create index, like create index on t of t, where 3 is, you know, whatever, t is greater than 3 or something. Or we can say, actually, we can do it inside of the table definition, like create table a int, index of a, where t is greater than 3. And this thing we didn't add support for the parser to, and I guess that's like how the optimizer happens to do the index table definitions, just because that's what it does, so we're gonna have to just quickly do that as well. Luckily, it's gonna be very easy, because we can just copy what we did the other time. We'll just go like this. And then in SQL.y, we have to do a similar thing. Create table. Wherever that lives, we have to edit that guy. Where are you at? Create table, create table, create table, table, element list. Where is the thing where you could potentially add some indexes to it? Maybe it's this guy, op table, elem list, table elem list, table elem. There it is, okay. So we can define a column, we can define an index, and this thing is the one that has to be edited, I think. Yeah. So we'll add this predicate guy to index def. Where did it go? And it looks like we add it using the opt where clause to the end, like so. Inverted indexes, do they get special where clauses? I don't even know. I think probably, but like I'm just not going to deal with that for now. Actually, we might as well deal with it right now, just because we can. But it'll just be broken until we fix it. partial index predicate, grab that guy, and then over here we just use it like so. And the number here is going to be 10. Or 11 in this case. And in this case, it's going to be 1, 2, 3, 4, 5, 6, 7. Yeah, this thing is a little janky, but whatever. That is not the problem of this particular stream. 7. Okay. Now I think if we maybe run this again, it'll do something different. No, we were actually going, if def.partial index predicate is not equal to empty, then we're gonna say table.partial index count plus plus. Doesn't like this. Oh, it's an expr. Yeah, this is just not going to compile, but it will if I try again, I think. And then I think we have to edit the indexes that actually get created here. So partial index predicate here is going to be a cat. Well, we can just do it down here. If we have a partial index predicate in our definition, then we're going to set the index's partial index predicate to, I guess we have to like serialize it again. I forget where we did that. Where did we do that before? Where do we set this thing again? Serialize, here it is. Tree.serialize expert. All right. Tree.serialize, we'll be serializing our definitions, partial index predicate. Okay, so I think this will set up our test catalog for success. Let's run the test again and see what happens. What? I did something dumb. 558. 558. Huh? I don't understand this quite. Test cat. Oh, whoops, I'm just in the wrong file. Test cat to log. Oh, right. We didn't finish doing this. So return tt.partial index count. Okay. More broken stuff. So it's in this add partial index predicate calls thing again. Add partial index predicate calls 727. Oh yeah, okay, we just did it, right. We were debugging, that was a side tour, a yak shave. We were debugging this and we didn't want to recompile everything from scratch. So now we are going to actually get to test it more easily is the idea. Oh, I see. The problem is that we're using I here. We have to use n partial index here because we don't have I partial index predicates. We only have some. This is a mega jam, right? Yeah, this playlist is absolutely sick. It's absolutely sick. It's called Organica on Spotify, if you like it. All right, so this is cool. Something happened, I think. Insert, so. Hey, this looks pretty good, honestly. So in our projection, we've got like I mean, oh yeah. We've got 3 because we don't have a primary key. Let's actually fix this test to be a little bit less gross. But otherwise, it's looking pretty good, TBH. Where did that test go? Let's give this insert into, whoops, what am I talking about? Partial indexes wants a primary key. That's what I'm trying to say. Primary key. 2 partial indexes. Well, let's just get a little bit smarter. We'll make 3 columns, and then we'll go like this. We'll do one of them where the predicate is on one column, the column that the index is on. And then we'll do one where the predicate is on other columns. Maybe we'll just do like all the columns just to be fancy. So index of C where A is greater than 0 and A is greater than B. How about that? And C, let's make this a string. Do we ever do things with strings in this file? Not really. But we'll just do it for fun. All right. This will look slightly different than what you were seeing from explained because it uses the build directive, so it doesn't run norm rules. So it doesn't do things like merging projects. You can s build norm if you want, but build is more directly when you're constructing, so it might be nicer. This seems fine. I mean, I don't really care. This looks fine. This looks great. Oh gosh, but what's the deal with this? This shouldn't be, they shouldn't both be called 1. Maybe I just forgot to like n++ in some loop. This is a good little thing to find. Mutation builder. In fact, I did not. Maybe it goes at the end here. Let's use this rewrite. So this rewrite flag is pretty cool. It'll just basically replace all of the output of all of the tests with what the program generates. So then I can look at it inside the file, and it'll be a baseline for the next time I run the test. This looks wrong. Why is this? What? Oh, no, this is right. This is right. This is right. We're good. Cool. Okay, so the next thing to do, I guess, is to like actually evaluate the Boolean and then do stuff. If we, depending on the value, probably. So I think what we want to do next is figure out where that happens for check constraints, which I think is what I was doing before Justin gave me a great idea to make everything a little bit better. Or I forget when I did that. This song is like, it's kind of intense though. I'm gonna skip it. So, right, in insert code, there should be something somewhere that checks this stuff. There's gotta be. There's gotta be. Process source row. Verify the check constraint results, if any. Yes. It's genius. Check set. Oh my gosh. This is absolutely what we need to start thinking about. Yeah, just absolutely true. Just absolutely true. Lots of stuff to look at here. We're gonna have to edit some optimizer stuff. Okay. Now, since I always forget where stuff lives in these special files that don't have Go suffixes, I'm just gonna go ahead and go like this and see where it gives me stuff. Where does it give me stuff? Mutation.opt. So I guess we want another thing here that sort of explains stuff. I love things like to do. We don't actually implement this optimization currently. Oh wait, this is the wrong file to be looking at. We want expert.opt. Mutation.opt. Yeah, all right. Check calls now gets another thing, and it's gonna be partial index predicate calls. Do we actually not? I thought we did. You're talking about this optimization. What is this optimization? Since the check constraint for column A can be statically proven to be true, check calls would contain... I'm not even following what's going on here, honestly. I see, it's an update case. Maybe it works in the insert case, but not for other cases. All right, partial index predicate calls. The columns from the input expression containing the results of what? Every partial index predicate for the mutation, for the target of the mutation. Each column in this list will be a Boolean column. Boolean contain a Boolean value that is true if the predicate is satisfied for a row, indicating that so what does it indicate? It indicates, I mean, for which, how does the output person know which index we're even talking about? That, I guess, I don't know. The index corresponding to this particular predicate requires an entry for the row. I guess. I don't know. I feel like I've written this comment like 12 times in different places, and it's all slightly different. I see, but the important sentence here, I guess, is this. This is what people are going to care about. Count and order of columns corresponds to the count and order of the target table's partial indexes. For example, A and we'll just do two. Yeah, I'll do three. A and B and C and index A where A is greater than 0. Well, index C where a is greater than 0. The point of this example is just to show that like this guy, even though it's the, oh no, we need another thing. We need this. We need to know that this guy, this third index, it's only the second partial index, even though there are 3 indexes. I don't know. I don't know if this is really even that important to document, but it probably is for somebody one day. In this case, the 0th column is the partial index predicate column for the index on A, and the first column is the predicate column for the index on C. Since the index on B doesn't have a partial index, or doesn't. I guess it isn't a partial index. Okay, that was a lot. Partial index predicate calls.
I don't want to be an emperor. That's not my business.
Okay.
I don't want to rule or conquer anyone. I want to help everyone if possible. Jew, Gentile.
Wow, this is kind of a wild quote coming over the headphones. All right, so I think if I maybe make now, it'll, no. Maybe if I make now, it'll like update stuff and then we can move on. All right, so the upshot is that now there should be generated code for these. Yeah, there they are. Okay, partial index predicate calls. Okay, so we'll start from building an insert, I guess. We'll see if this is the right place to start. I don't actually really know. I think we probably need to check to see if this thing needs updating. My guess is that there's some... Can you do a fast path insert with checks? Is this the same kind of check that we're talking about even? Or is this like a foreign key check? No, this is like a completely different kind of check. Okay, we'll ignore that then. We'll ignore that. Wait, but is this one? Dude, that's confusing. Over here we have something called checks, and it's really about foreign key checks. And then over here we have something called checks that's really about check constraint checks. Yeah, I don't know that this playlist, I feel like it's gotten into a bad place. I'm gonna skip that one too. But I guess the upshot though is that like you can still do fast path stuff with check calls because this whole thing is set up over here. So yeah, we'll just continue on then. We'll start from here. We'll add extra slots in our call list thing, whatever that is, for our partial index predicates. We'll add them. And we also have to populate them, right? So this is an odd place to start because we actually haven't populated anything yet. What could this be? Ordinal set. Construct. I don't know what this is for. Values.calls. I don't know what this is about. Let's ignore it. Okay, but the point is though that we're gonna edit this guy, which is only using one place. That's nice. Oh, it's an interface. I can just use this little thing though. And we're gonna add check ordinal set. Why is that different from column ordinal set? It just like is for some reason. That seems really random. I don't see the point of that in the slightest. I'll just use a column ordinal set. Oh, did I put it in the wrong order? I probably did. Gross, gross, gross. This would be better. Okay, now over here, we're just gonna pass in our calls. And then this should be happy again. And this should be happy again. Maybe it'll, no. Too many long lines here. I think the best way would be to give everything its own line. I wish that Golang would do this for you. I don't know why it doesn't. I don't know why I'm doing this by hand. It's horrible. Okay, so we pass this stuff in, then, but yeah, the question still is who is supposed to be setting this stuff, really? Who is setting this stuff? Is it this? I think that the editor should tell me who's setting it as opposed to who's writing it, right? What happened to that? What? Press this complicated thing to search again. No. Where's that? I forgot the shortcut for this search guy. The like fancy search that gives you the better window. Find usages. Where's find usages? Why do I not remember how to do this? Command F7. Right. How could I forget Command F7? Value read, value write. This is value read. This is value read. They're all value read. What? Excuse me. How does that make any sense? How does that make any sense? How could they all be value read? Oh, right, because I just added it. We have to do it for the one that, oh my God, that's embarrassing. Okay, value. What? Okay, consider me confused again. Option F7, guys. It's not Command F7. Okay, here we go. Here's the write. It happens one time in Mutation Builder. Okay, that's cool. That's sort of where we were before. So that's a good thing to know about. We're gonna make some things and these, okay, right. Okay, so this is where we're linking this stuff up. That's good. It's pretty simple. Pretty simple. So our mutation private now has the right call list. That's fun. Then we run this thing. These guys get consumed, and then our factories will need to learn about them, I guess, next. What happened to this here? What's going on with this? Return, I renamed them. Insert, call, ord, set. Aha. So this is where everything is coming together, and now our insert run thing, which is actually the execution code that is going to be hooked up to this, needs to get an equivalent field. This is yet another example of check being overloaded to mean both foreign key and check constraint. I don't love that. I do not love that very much. Yeah, I'm thinking because what's kind of confusing about this is that we're going to be storing this ordinal set that indexes into the number of partial indexes. But the thing is that we don't have access to only the partial indexes anywhere. So I'm wondering essentially whether I want to be making another slice in the immutable table descriptor that caches all of those so I can look into it efficiently, or if that even really matters at all. Or is it inefficient to create the slice in the first place? I kind of think that we should create the slice because it's only going to happen when we have partial indexes in the first place. Maybe. I don't really know though. I'll do that though. Yeah, okay. I'll do that. I guess. Do we have anything that like keeps weird pointers into slices or something? Maybe there'll be ordinals into the public and non-public indexes. Is that what we want to do? How about we do that? We'll try that out. So this is going to be changed now to be partial index ords. Partial index ords contains one ordinal referencing the public and non-public indexes slice. Referencing? Yeah. For every partial index in the table. That's going to be a slice of ints. And then instead of updating this thing, we're going to be actually just like, oh, but it's, yeah, no, I think that's actually good. We'll be essentially saying desk dot partial index ords equals append desk dot partial index ords comma I. And then over here, we'll do the same thing. I guess in this case, we'll probably want to, yeah, do it, just duplicate the code in both of these loops, because otherwise it'll get out of sync. So if desk dot, or if idx dot partial index predicate is not equal to empty, then we'll add our partial index ords thing here. And likewise down here. And we can get rid of this whole thing. And then over here, we can also get rid of our index count and just return desk dot partial index ords with a length. Okay, I think that's going to be better in the long term. Okay, so anyway, back to our insert code. I think we're going to have a new partial index predicate ords thing. And we can make, I guess we'll make this a new type, because like, why not, I guess. We'll call it index set. Partial, I don't know, dude. Partial index predicate set. It's just, it seems really pointless. I guess the point is that like the type specifically references ordinals into something else, so you make another type for it, I guess, but it seems a little silly. So it contains a subset of partial index predicates as ordinals into immutable table descriptor dot partial index predicate ords. No, partial index ords. Wait. I'll have to make a new method for this as well. Maybe we should just make this thing return the whole slice. Yeah, we'll do that. Partial index ords. What? I don't know. Is this right? Yeah. I think this is good. So this is returning a slice of int. It's going to return des.partial index ords. Returns a slice of ordinals into desk.public and non-public indexes, one per partial index on the table. And this is going to return the length instead. And then here we can say as ordinals into immutable table descriptor dot partial index ords. Partial index ords. These each ordinal, each predicate has a Boolean column produced as, I mean, I guess theoretically you don't have to always produce all of them or something if you're only updating a set of the thing, but that seems like super complicated. Maybe that's kind of like what that earlier optimization question was about, but I'm just not going to mess with that. Each predicate has a Boolean column produced as input to mutations, indicating result of evaluating the partial index predicate. Yeah, I think this is probably what this is about, but like, I don't know. It's a little cray. Yeah, I think I'm gonna leave off for now though. I think this was good. I liked this setup a lot. I could actually do stuff because the computer wasn't laggy. But yeah, I gotta go do some other stuff. But I think this was pretty good. Good progress. I think next time I think we'll get a lot done if we keep working on this, and assuming I don't work on it at any other time. I think we'll get pretty far. I think maybe we can get the execution part totally done next time. And having thought about the predicate stuff on the optimizer side, I don't know. I feel relatively confident that I can figure out how to do it. Maybe there's complications I haven't foreseen, but I think we're well on our way. Yeah, thanks for sticking with it, guys. I appreciate the watching. GG. Yeah, GG. I think, okay, I'm going to try something new this time as well, which is that I'm going to attempt to see if there's any other programming streams available on the internet so that I can raid them, so that I can build my followership, you know? Like maybe if I bring my 5 viewers, you dedicated, wonderful fellows and fellettes, to the other stream, then maybe they will, watch my stream, maybe. So how do I do that? I go to this thing, maybe, and then I'm gonna click this. Oh no, but I don't see any programming streams. That's really problematic for my strategy here. Super problematic. Well, I guess, hold on. What if there's secretly somebody that is streaming programming and I just don't follow them? Is that a possibility? Let me see if that's a possibility. Let me see if that's a possibility. Just stick with me for a second, because this is going to be sick. If I can figure it out. How about this seems cool. A random project in Rust person. I'm going to do this. This is going to be really fun. So boom, we hit the follow. Boom. Go over here. Boom. We hit the raid. Wait, maybe we have to refresh. No, I don't know. I don't know. I don't know. Wait, what is it? Muse on. This seems like a really cool person. Check it out. We're gonna raid him. All right. Yes, 2 viewers are ready to raid. Maybe 3. Okay, well anyway, enjoy guys. Thanks so much for following. See you. Did it work? Not sure if it worked.